This video is quickly going to go over connecting a Cognex camera to a ABB robot via robotstudio rather than the Cognex Insight software. So, starting off, we'll open up robotstudio and pick one of our virtual controllers. Now, we're going to wait for this virtual controller to completely start up, but while that's happening, we can open up the integrated vision tab. And one thing I want to point out why we have this open is going over to the controller inside the left tab and then going to controller and options. We want to look through our options and check and see that we have the integrated vision add-on. This is the only way for the robot to talk directly to the Cognex camera in a kind of pre-packaged solution. If you're not using this, there are other methods, but they do require a little bit more work. All right, so because we opened up that integrated vision add-in, we will have this tab up top that says vision, and we can look at the controllers on the robot. Now you'll see that this robot has no controllers and cannot connect to any right now. So if you are online with a real controller, you can use this add sensor setting and add one of the sensors that shows up right here to the network. You'll also be able to change IP address and set all the other details. One thing you'll notice, and you may need to hit show all, is that I don't have any connected to this computer at this point. So I'm actually going to start up a virtual Cognex camera. So I'm going to close this out and I'm going to open up Cognex's Insight software. Now you can get a free emulator key from Cognex. You just have to sign up with an account and it's a pretty reasonable deal. So I highly recommend it, and then you'll be able to program Cognex cameras just on the software. So I'm going to go ahead and minimize the Insight software. And now that I have done that, I will have an emulator running down here. If you want to, you can select a specific emulator or just go with a standard option. I'm going to go with the 5705 because it's one that I've used often, so it's very convenient. After you've gotten to that step, you can just minimize this and you won't need to mess with it anymore. So if I go to this Vision System tab and hit Refresh Cameras, I now have an additional camera located right here. I can right-click on that camera and hit Connect. Because this is a virtual camera, the only way to actually work with it is to load images. So I can come in here and click Load Image and select a random image. There we go. From other pictures I've taken on my computer, this isn't a great example of trying to use a vision task for, but you do have this as an option. So once we've connected to it, in order for the robot to actually be able to use it, you do need to rename the camera. Renaming this camera is what connects it to the robot and lets the robot know what it needs to connect to. So I'm going to call this emulated camera. No spaces allowed, of course. We'll hit OK, and then we'll ask me to restart the robot, so we're going to go ahead and let that happen. Now, inside of here, I want to show a few things. So whenever you're using an emulated camera, you cannot acquire an image or show a live video, but you can still set up the image. So talking through this a little bit, setting it to camera will allow the robot to be able to trigger it with the standard Insight commands and integrated vision commands. Selecting the trigger as camera will allow the robot to trigger it using just the standard integrated vision commands. Trigger delay is once a image is requested. This is how long it'll delay the picture. Exposure is how long it allows light in. The longer you turn that on, the brighter the image will be, but the more likely you are to get fuzzy or blurry images if something moves. Going on from there, you can also calibrate the camera. So calibrating a camera is how you coordinate the robot and the camera together. From there, we are going to create a just basic max pattern detection tool and make it very simple and say we're looking for this gray box. I'll now hit OK, and it'll search and find it. So a few settings to watch for in here is we have pattern 1, the tool fixture, tool enable. So tool enable will mean that is the camera actually searching for this pattern or not. The tool fixture, if you have multiple patterns you're looking for, you can relate the patterns together. And then the last one is just what name you want to give it, and that is just for organization's sake and making it a little more readable. Inside of the settings tab, we have the acceptance threshold, which is what percentage or how well it has to match for it to count it. The contrast threshold What this does is it is looking for the difference on edges before it recognizes it as a contrast. So if you have items that go from a gray to a black, it's going to be able to deal with a lot less contrast than something that goes from white to black. So that's one setting you can change if you have items that are coming out for fuzzy or having other issues. Rotational tolerance, that is how many degrees out of whack it can be before it will not find it anymore. Scale tolerance is if you want the item to be able to grow and shrink, you can use the scale. Now it is a percentage of it, so if I hit 1, that means that it can be plus or minus 1% of the original image. Ignore polarity. What that does is whenever you have an item that goes from black to white, or it can sometimes go from white to black, you would be able to ignore polarity, saying that it will recognize both transitions to find the part. Location tools are typically what you end up using on the robot. However, there are exceptions to that sometimes. So, all right. Just to talk through a few of these tools, circle tools does exactly what it sounds like. It just locates a circle. The problem with the circle tool is that it will not locate any random circle throughout an entire image. It only looks in this one location. So what you often have to do whenever you're using the circle tool is link it to another tool. So earlier we were talking about having a tool fixture. This means that if pattern 1 gets moved, then the circle gets moved with it. So if I come in here to pattern 1 and start playing with things, so I can start adding horizontal and vertical offsets, because right now you'll see pattern 1 got located with its coordinate system right there in the middle. Maybe I want it lined up to that top edge. What I can do is start adding vertical offsets to try and line it up, and you'll see the circle moves at the same time because it is tied to fixture 1. And then we'll go ahead and do the same thing to the horizontal just so it looks pretty. So we'll go ahead and talk about a few more of the important location tools that I use a lot of times. So we have circle, the max pattern, the red line variant, and then the other variants are just different algorithms that are used to find it. So you'll have to test for your application and see which one works best. I do often use the max patterns that are 1 through 50 or even 1 through 10 sometimes. And then that's typically all I end up using inside the location tool. I have used the blobs in the past. If you're getting into complex jobs, you can start using edges and edge intersections, but once again, that gets to be a little more complex than what I'm idealizing here. Inspection tools are exactly what they sound like. They're only for the purpose of inspecting items and checking that they're there. Now, it does give you the ability to calibrate items, but for the most part, we are not going to be messing with that. Now, the next step is getting the patterns you made to export to the actual robot. So what we do is go to the controller over here on the left-hand side, go down to Vision System, and then select the camera that you're working with. So I'm going to select this emulated camera, and now I have this output to rapid option. What this does is it lets me choose what is sent to the robot code. You'll see what I mean by that because it writes it to a specific type of robot variable. Now, I'm going to choose pattern 1 as my variable, and it will automatically let me go ahead and do X, Y, and the rotation. So because this is a camera, I only have X, Y, and the rotation about the Z axis available to me. If you need to pass additional information, such as whether the job failed, what the status of the job is, and any other details like that, that's what these additional values are for. But for ours, we are not going to do that. We're just going to pass a fixture for the time being. So after we're happy with that, we'll go ahead and save the job and just save it anywhere. Now, most of the time, whenever you're working on this job will actually be saved onto the camera. It's important to remember that the camera is effectively a computer of its own. All right, from there, we're going to go ahead and toggle mode, and this will put the camera into run mode, meaning that the robot can communicate and control it. All right, now that that's been done, let's go ahead and hop over to the robot code and give a good example of what this code can look like. So I'm going to create a new module and call it the camera module. hop over here, and inside this camera module, whenever you're working with the camera for the first time, I highly recommend going over to the Rapid tab and hitting drop down on Snippet, and there are some pre-made integrated vision options. So we are going to do a move to detected object, and it auto fills out a lot of this information for you, making your job significantly easier. So I need to rename the string that is my job file. It will now be demo program.job. Instead of my camera, it is emulated camera. And that is the same as this name over here in the integrated or inside the vision systems tab. And then my work object will go ahead and bring that declaration back in. My Rob target, why not that one as well? And even my tool. All right, so to walk you through kind of what this program is doing, this routine will set the camera into program mode and then load the job that you want it to load onto the camera, and then it will put it back into run mode. The robot can only request images, get results, and actually control the camera per se whenever it is in run mode. From there, you request an image. You're going to get the results of the image. Now, one thing to note here is if your job fails and you try to get results of an item that doesn't exist or has no results, it will get stuck on this line and never continue past. So it is sometimes best to add a max time of 5 seconds. If your job's taking more than 5 seconds, that is an extremely complicated camera job. So you may want to reevaluate that. And then we get into the coordinate system transformation. So we'll dive into that a little bit more and try and explain that here in a second. And then the last step is you just move to your robot target. Okay. So I'm going to go ahead and toggle this back into program mode just to play with it. So if we look at this code, it actually does a pretty good job of explaining how this is supposed to work and what you need to do in order to make this routine work. So one of the things I want to point out, the steps needed to set up the camera. During the first cycle, so whenever you take that first image and you run this program for the first time, you're actually going to have to set the MyRob target. All right. With that, we're going to hop into trying to describe the coordinate systems that link these two together. Go over to the Vision tab, and we are going to calibrate this camera. For that, it does have to be in program mode, so we're going to flip that over, and we are going to do a grid calibration. Now, the purpose behind a grid calibration versus the others is it allows us to define the coordinate system of the camera. I'm going to tell it to print this file, and I'm going to tell it to print, but I just want it to print to a PDF. Now, what I'm going to do is I'm going to take this fiducial and I'm going to save it as a JPEG so that I can load it into the camera. All right, so I'm going to go ahead and load that image onto the camera. And now that it's loaded, I can continue with the calibration steps. So now that we have a picture of the calibration file, we can hit next. And because we have a picture, it'll automatically start looking for where the corners meet up in the image. It is expecting an even spacing based off of what we had the grid spacing set to. So it's important to make sure that what you have this set to is what actually got printed. It is possible for printers to automatically scale your papers, resulting in it not working. So please be very wary of that. So now we're going to hit set. We're going to make sure that it found an adequate number of points to calibrate based off of. Now you want this calibration to take up as much of the field of view of the camera as possible, which is why you do have the option to do multiple poses, meaning that you calibrate more areas of the camera. So I'm going to hit next again because it looks like it found an adequate number, and hit calibrate. And it looks like it did an excellent job calibrating, probably because it is a completely virtual answer, but that's beside the point. Typically, if you're below 2, I would say that's an acceptable calibration for most robotics applications. Once again, that depends entirely on your accuracy, the field of view of the camera, and how far away you're actually working. So now that we've completed the calibration, we are going to want to save this job one more time. Whenever you save the job, it is saving the calibration with it. So it is very important to remember to save that job. Now, what has happened is the camera has located the origin of this entire camera onto this dot right here. It has also, oh, sorry, that dot. And the x-axis is defined this direction, and the y-axis is defined this way. Now, typically, this piece of paper will be mounted onto a tabletop or something similar within the robot's reach. So, the reason I bring this up is the camera has created its own coordinate system located at this point with the x-axis that way and the y-axis this way. Right now, the robot has no idea where the camera is actually located. The way that you end up doing that and locating the two relative to one another is teaching a work object at the same location on this piece of paper. So it's very important to not move the piece of paper between the time that you calibrate the camera and the time that you create the robot work object. I cannot stress that enough. This is the only time at which the locations get linked together for the camera and the robot. So please be very cognizant of that. Now, we're going to hop back over to the rapid side, and I am going to bring this work object into the virtual world real quick by synchronizing. And we'll see that this work object by default got placed in a very annoying location. So we are going to start dragging it around and put it somewhere a little bit more sensical. So what I'm saying by putting the work object right here is that the fiducial, the piece of paper, was mounted on this table with the x-axis pointing that way and the y-axis pointing this way. And whenever you teach that work object, you will typically take a spike or a calibration tool and put it on the end of the robot and physically go touch the 3 points on the fiducial. Now, I want to go ahead and explain how ABB defines their work objects. So we're going to hop over to the controller tab and bring up a virtual pendant to talk against and explain kind of what we've got going on. I'm going to jump over to manual mode. That way I can play with the robot a little bit more without it getting angry. And go over to the jogging tab. Whenever you're teaching a work object, you're going to be in this jogging menu under work object. And then just for the giggles of it, we are going to work on my work object, edit, and we will define it. So whenever you're teaching a work object for a camera, you always want to update the user method. So to explain how ABB does their work objects a little bit more in depth, the object frame is in relation to the user frame, and the user frame is in relation to the world frame. So what I mean by that is if I have the user frame set to the XYZ value 100, 100, 100, and the object frame set to the values 50, 50, 50, that means that the actual ending work object will be at 150, 150, 150, assuming there are no rotations. Once we're back over on the simulation side, I'll show you a little bit more of what I mean. Whenever you teach these first 2 points of a work object, it defines the x-axis of the coordinate system, but it does not define the origin. Whenever you teach the y point of the work object, what it does is it draws the shortest line between the y point that you just taught and the x-axis. That is where the origin will be, and that line will represent the y-axis. Now, assuming you've taught the work object and you've only taught the user frame, if this is an object that has been used before, you may want to come in and change some values and make sure the object frame, also called the O frame, is set to 0 XYZ and 0 rotation, just to make sure it doesn't mess up any work objects you may have taught. Now, I want to go ahead and provide that example of how that work object is actually taught on an ABB robot. So, the nice part is they do allow you to create frames using that same method. So, I'm going to create a frame using the 3-point method. which does the first point on the x-axis, the second point on the x-axis, and the last point on the y-axis. So what happens is I will teach the x-axis real quick, and I want it to snap to the endpoints of lines so I can make a nice pretty thing. I'm going to teach x1, clear over there, x2, clear over here, and y1, clear up here. Now, on a lot of robotic systems, what defaults to happening is the origin is set over on the first point you taught. ABB does not work that way because sometimes you cannot teach the point where you want the origin to be. For example, I would not be able to be very accurate when trying to teach an origin in the middle of a flat plate like this. But because I'm able to teach a point on a nice flat, sharp edge, rather than on the flat plate section, it can allow for greater accuracy. There's nothing stopping you from using x1 as the origin, but you do need to remember that y1 right here is actually what decides where the origin will be. So in this case, it will be slightly offset to the left-hand side. And x2 is just the direction for the x-axis. So I'm going to hit create, and we'll see it creates a frame right there with the y-axis lined up with that y point, but that first point not actually being the origin. So the reason I wanted to do that is I'm going to go ahead and move my work object over to that frame we just made. So I will attach it to the frame. Alright, so I've now taught that work object, and I'm going to get rid of that additional frame because it's no longer needed. And then I'm going to go ahead and mess with this work object more so that I can show a better example of how the object frame versus the user frame works. So I'm going to rotate this about the local z-axis by 180 degrees. There we go. We'll see why I did that here in just a moment. Alright, so I'm going to start messing with the values on this by hitting Modify Work Object and typing in offsets. So the user frame, if we click on the values, have already been set. That was done whenever we taught the 3 points. The object frame is not typically used on ABB robots unless you're working with the camera or doing something else that benefits from it. Now, with that said, if you teach the object frame instead of the user frame, your programs will work just fine. It just may lose you functionality in the future. So, that's one reason to try and stick with the user frame. Alright, I'm going to come in here and start modifying the object frame values. So I'm going to type in a 100mm offset in the x-axis. What we'll see is it actually moved the coordinate system in the x direction, but not in the robot x direction. As I said, the values are relative to the user frame. So you'll see that it got shifted backwards, actually, compared to the typical robot frame. Now, the reason that's so important is because when we're working with the camera, the x-axis of the camera does not have to be the same as the robot's world x-axis. It can be whatever it wants. So, this object frame is what we actually use to track the different parts. So I'm going to synchronize all of this stuff we just did to the virtual controller. So we're going to synchronize to rapid, not the station. And hit OK. I'm going to go ahead and also flip the robot back into auto mode. So we'll see it went ahead and updated the work object data here. I'm going to jump back over to the vision stuff and take a new picture. So I'm going to go ahead and load that other image we took earlier where it can actually find something. So I'm also going to delete the circle since it is unfindable at this time. And we'll see that pattern 1 is still completely visible, and then save that job while I'm at it and toggle that mode. So if we jump back over and we look at the values, -48, +67. That is in relation to the calibrated values we did earlier. So if you remember, whenever we had the calibration grid opened up, it was approximately clear over here. And once you go -40 in the almost -50 in the X and +67 in the Y, you'll end up with the location of those little green arrows. So I'm going to jump over to Rapid, and we're actually going to run this code step by step. So now I'm going to start tapping my way through this program, hitting F11 to run it one step at a time. First, it's going to set the camera into program mode. That way I can load a camera job. So a job can only be loaded whenever the camera is in camera mode. The next command we're going to send the camera is a request image. Now, we are working with a virtual camera, so it is going to be important that we hop back over to the Vision tab and load an image. So I'm going to load just some other old image. I'm going to go back to Rapid and continue hitting F11. And it will get that result. Now, whenever we hover over the My Work object, we'll see the object data, which I'm going to go ahead and add a watch window to so we can look at a little more closely. These first set of values, this XYZ and quaternion or rotation value, haven't really changed, but over here, so this XY position is the frame location in the camera coordinate systems. If we hop back over to this emulated camera job and zoom all the way in, oh, maybe not that far all the way in, we'll see that it has added a little coordinate system right here. Now this coordinate system and the values it outputs is relative to the calibration that we did much earlier in that fiducial. Now that we've recorded that position, we can go ahead and also record the MyRob target. So I'm going to go back home and make sure everything is nice and synchronized. And I am going to reset this MyRob target in my tool just so that the robot can actually reach it. I'm going to make it so it's been rotated 180 degrees about the x-axis. And it will now let me run that routine. So I'm going to hop back in here, go to cursor, and hit F11 a few times, and we will see where the robot actually goes. Now, earlier we did go ahead and set this camera work object over by the table, and it needs to be resynchronized. There we go, my work object. There we go. That is clear over here, and I'm going to swing this robot a little bit closer. That way it will run just fine. So now we can run back over to Rapid and try and run this again. So PP to cursor, F11, F11, and it does not want to move because whenever I set this position, first off, it just has constant values typed in. But the bigger concern is the configuration data is all incorrect. Just to show you guys what that looks like with it running, we're going to disable the need for configuration data right now and call it good. Hit apply, move the program pointer back up, and step through. And the last thing it's angry about is the undefined load, of course. So I'm going to hop up here and make sure that our load data has something in the Z direction. And here we go. There's always something new. So this one does also require external access values, and I happen to know that the external access values are going to be 0 and 0. So one more time, we're going to rerun this routine. And hopefully it takes off. And we'll see that the robot is aiming for the typed in target that we have. Now, the super important part about using the dual work object method. Instead of writing the camera target directly to a robot target, it's best to write it to the work object, because whenever we have a camera rotation that is not 0, for example, if I come in here and say that the robot should always approach from the X direction of that part. So this might be the example of making sure we're sliding onto it, or maybe our grippers can only approach the part from one direction. And if the part is expected to rotate, we may have to match that rotation. This double work object really gives us the ability to approach the part from a consistent direction, even when the part is rotating. If you just feed it the XYZ values, then you have a problem with weird rotations. So let's go ahead and run this again. And just to show you what I mean, we're going to come in and so we'll see it approaches it from the X direction in that simulation. It moved from right to left. However, if my camera target, so I'm going to come in here and manually change the camera target. I'm going to say our camera target has a 90-degree rotation about the Z-axis. So don't forget, camera rotations will only ever be about the Z-axis, never the X and Y, because it is a 2D camera that you did calibrate to a flat plane. Oh, looks like I'm missing one more set of brackets. There we go. So I went ahead and typed in a manual rotation about the Z-axis of about 90 degrees. So if we watch this, now the whole robot will approach from the right, and if I switch the direction, it will approach from the left now. Oh, I've also been skipping a step, so we need to go up one level. So, as long as we write this camera frame to the work object, now the robot will no longer approach from the right, but from a different direction, actually. And then we can rotate negative, or in the opposite direction about the Z-axis, and rerun this same routine. And we'll notice that the robot will swing to the other side now. Now, we did go ahead and let joint 6 wind up just a little bit too much, so that's why that one errored out. If we just get a little cheeky here and spin joint 6 back around so it's not causing issues.
We can go back to Rapid and run this same code. And we'll see it comes from the other direction now. That is really the biggest benefit behind teaching the robot the different coordinate systems and using the camera data and loading it straight into the work object rather than doing complicated offsets and multiplications that you would typically try and do on other robot brands. Hopefully someone finds this useful. With that, I'm going to end this.